Okay.
Now let me just get my screen going. Entire screen. Let's see. Can you see that okay?
Yes.
Good. Because if I remember rightly, what we need to do is we need to do that and then full screen. How's that?
That looks good.
Okay. Excellent. So this talk is basically about using the JVM as a platform for building smart contracts. And normally at this stage, I would ask you to put your hands up if you know a bit about smart contracts or would consider yourself an expert or have maybe played with Bitcoin or Ethereum a bit. But of course, now that I've got my my screen share up, I can't see you. So if you can put your hands up, and if Tim, you can tell me roughly what percentage of the room is putting their hands up to the question: do you consider yourself to be fairly knowledgeable or an expert about cryptocurrencies or smart contracts?
I think I saw about three hands.
Okay, so a few people. Okay, for those people, please don't kill me for some of what I'm about to say in this talk. That's good. I'm glad there are some experienced people in the room. But this talk really is designed to be, well, kind of introductory and accessible, even if you don't have a huge background in crypto or smart currencies, smart contracts. But at the same time, I also want to focus on one specific aspect of it, because my interest in cryptocurrencies and smart contracts is not, I'm not necessarily one of these people that thinks that they're going to completely change our economic systems or change the world. I'm kind of interested in them from a technical and computer science point of view, and also just from what they show us about human social dynamics. So those are my main interests. So my take on it is probably a little different to a lot of people that are involved in the space. Okay, so a bit of background about me for people that don't know me. I've been involved with the Java community now for around about 9 years. I helped to organise the London Java community, which is one of the large and quite influential communities globally. And I've worked on various programs with the LJC and kind of helped to, as part of a steering group. I think much like your user group, we rather than having one individual person that tries to do everything, we have a reasonably large team of people that help out, and I think that basically helps for continuity of the community. I've since being involved with the LJC, we've actually won an election to the Java Community Process Executive Committee. So that means that I've had a ringside seat because I'm the rep who goes to the meetings for the EC, and we've seen up close and personal all the mess over Java 9 modules and all of the voting problems and all the disagreement about that's been in the tech press so recently. So I think it's great that you guys are going to do some more Java 9 work with your user group, because it is still badly needed. Just as a quick throwaway, if you look for a recent article by Trisha G, she's got a great article about doing Java 9 modules, and it's a fully worked example with a load of really, really good stuff in it, not just the module stuff, but a bunch of other things as well. And the most recent issue of Oracle's Java magazine has had a big push about Java 9, and there's more coming in the next edition as well. So the current issue and the next one, if you're looking to do some Java 9 stuff, they're great jumping off points, as well as Trish's article as well. So I think if you were short of ideas or looking for something, that'd be a great place to look. So that's basically the community stuff. I've been elected a Java champion and won the Rockstar Speaker Award a few times as well. On the commercial side, I've spent most of my time in gambling houses and banks, and you can probably make your own jokes about similarities between banks and gambling. I couldn't possibly comment. So I guess my interest in cryptocurrencies and their applications to financial technology has really also come from my history of working with trading systems and trying to figure out what these things really are. Okay, so that's the background. So what are we going to talk about today? Now, what we're going to talk about is we're going to talk about the computer science angle that cryptocurrencies have, and where we kind of get this idea of a smart contract form. What really is a smart contract? And then from there, I'm going to talk about the JVM and why the JVM might be a useful platform for building cryptocurrencies on top of. And then basically having done that motivation and said why we might want to do this, and talked about some of the problems that the JVM has, and how we get around them, and how we come to the conclusion that the JVM is a sensible place to start from. That's the introductory section, and then after that we get to the more technically heavy section of the talk. And I hope I'm not going to lose too many people, because there is some fairly low-level hackery that we're going to do. We're going to talk about bytecode, and we're going to talk about class loading. And then towards the end, I'm just going to kind of bring the threads together and talk about what was the point of the research, and introduce some technology which I think does move on the state of the art in cryptocurrencies in one small but important way. So that's the overall plan. If you're looking at this, then you can probably guess what area of computer science we're going to talk about. There's a huge clue on this slide. So we'll come to that soon enough. Okay, so let's kick off by talking about cryptocurrencies in general, kind of set the scene, and introduce some of the computer science problems that go along with the area. The first and most well-known of all cryptocurrencies is, of course, Bitcoin, which has been in the news for some years now, partly because it's so it's just an odd thing. It keeps coming back up. It's been known, of course, for especially for ransomware. And this is BitLocker, which basically will encrypt your Windows hard drive and prevent you having access to your documents until you send them some Bitcoins to an address. And that's kind of one use case, but not necessarily the ones that Bitcoin advocates would like us to think about. So it is a well-known one, but perhaps not the best. But let's take a step back and let's think about what Bitcoin really is. It's trying to be online cash, and what does that phrase mean? What does it mean to have an online-based system that behaved like cash? Well, if we look at the properties that cash has, I think that something that behaves like cash that was online should really have this kind of set of properties. These are what the non-functional requirements of a cash-like system should be. And you can't duplicate it, but it's anonymous. It's fungible. You can exchange it for anything you want to, and it's liquid, and you don't have problems using it places. That there is a fault-tolerant network. That one is really a function of it being online. Of course, you don't need a network to spend cash, but if we're doing anything which is internet-based, we are going to need one. So the network had better work. We should also have the ability that you can transact between anybody who wants to use it. If I go into a bar, I don't need to know the barman, and he doesn't need to know me for us to be able to do a transaction. I've got money and I want beer, and he's selling beer and he wants money. Now that transaction is completely independent of who each party is, and we don't really need to know that much about each other. And then something else, which also is a function of that this is online rather than physical, is that if we have a network which is going to carry these transactions, it actually can't prevent people from using it. So basically the capability of using online cash should be the same as cash, i.e. that it is accessible to everyone. Okay, so this is my set of properties. I mean, I think people who are experts in cryptocurrency might be able to debate the finer points of a couple of these, but this is targeted at people who may not have thought about this. And normally, if I was here in person at this point, I would hold up a £20 note and my debit card, because the point is, I don't know if you've spotted this, but if you look through this, sure, cash has these properties, but actually your payment cards, especially credit cards, actually don't have this. And all this time we've been using cash and using debit and credit cards as though they were really two forms of the same payment. And they're actually really not. Debit cards and credit cards actually are far more restrictive than cash. And what's happened is that those payment networks, because they're denominated in pounds or dollars, but we think they're the same payment system, and actually they're not. What they are is a big private network between the banks with protocols for banks to clear between each other, which basically has a ledger which records who owes what to who, and does a settling up process at the end of the day. Is it anonymous? Well, no. If you take part in that network, the bank certainly knows who you are. Is it fungible and liquid? Well, they've tried very hard to make make card payments accessible and available everywhere, but there are still plenty of places where you can't use those. Is the network fault tolerant? Well, again, a large amount of engineering effort is expended to make it as tolerant as possible, but it does still have substantial outages. And it's actually very difficult to make a network which relies upon individual physical locations be fully fault tolerant. So again, sort of, can you use it for transactions between parties that don't know each other? Well, sort of, but while the endpoints, the people doing the transaction nominally might not know each other, the bank certainly does know both sides. So in terms of the centralization of the information, the transaction is completely known to the network, even if the endpoints don't know each other. And then, can the network prevent people from using it? Absolutely. If the people that own the network decide that they don't want your business, good luck getting a merchant account. So there's all of these aspects of this, which mean that whatever network we design for online cash, it will look quite different to what we conceive of as banking payment systems. There's one other thing which I also want to drag out here, which is the first point, which I haven't spoken about yet, which is that you have to not be able to duplicate and spend your online cash twice. Now that point is actually a little more subtle than it looks like, because what it means is that whatever a digital coin actually is, we know what it's not. And what it's not is simply a special pattern of bits. Because if it was a special pattern of bits that somehow corresponded to a coin, you could easily duplicate that and spend it as many times as you liked. So in fact, the thing which corresponds to an amount of money has to be something else. And of course, what it turns out is that we borrow the ledger idea. That we have a number of addresses which are effectively like bank accounts, if you like, and they hold balances in them. And what you transmit to the network is a cryptographically signed proof that you own that endpoint, that address, and a set of instructions for what to do with the assets which are held by that address. So that's really what we're doing. Rather than actually having something which is a pattern of bits that represents a coin, what we actually use are addresses to hold assets, and then have cryptographically guaranteed instructions which come in to move them from place to place. Okay, so for people who understand a little bit of public key crypto, you can probably imagine a basic protocol for how we would cryptographically secure the instructions which get sent in. So this is now it's as similar to cash as we can make it online. There are of course some differences, like the use of the network, which is essential because we're network based, but it's also quite different from existing payment networks. So that's kind of, if you have never encountered or never thought about what a cryptocurrency looks like, this is really sort of the 2-second version of it. So Bitcoin basically solves a bunch of these. It solves the double spend problem. It solves the trustlessness and the anyone can use it problem. And it does so in quite an interesting way, which brings in some interesting aspects of computer science. The one thing it doesn't fully solve is the anonymity. Instead, Bitcoin is what we would call pseudonymous, which means that the network of transactions is all completely public. The only thing which you don't know is who owns the end addresses, who actually owns the bank accounts which are holding the assets. Okay, you can see money flowing through the system. You can see every move that everybody makes from every address to every other address, but you don't know who owns the addresses. So what that means is, if you can, by some other means, some network analysis, figure out who owns the end addresses, the whole security of the system, the whole network for those addresses becomes completely transparent. So that is, you know, potentially, and many people who are interested in the privacy aspects, that's a really bad thing, because it means that all it takes is some bad operational security about the who owns the addresses, and it exposes a large chunk of the transactions of the network. And there was a paper that was written recently where someone basically tried to analyze, by scanning social media and email dumps and data breaches, to try to figure out who owns which Bitcoin addresses. And I think through publicly available data and leaked data, they were able to identify ownership at least up to a social media username or an email address. They were able to identify the owners of over 15% of all Bitcoin addresses. So for something which is supposed to be, you know, anonymous, dark cash, that's not great. Okay, so Bitcoin is what I would call an interesting experiment. It's shown that this stuff can be possible. It's certainly had its drawbacks, but it's certainly, you know, from a technical achievement point of view, absolutely fascinating. And there's this quote from a guy called Richard Gendall Brown, who's one of the CTOs of one of the Bitcoin firms, who basically encapsulated this with the idea is that Bitcoin taught the world how to transfer value from place to place with no trusted third party, no you know, proprietary banking network of any kind. And that's not a small thing. That is a significant step forward. But is it the whole story? Well, the jury's still out, but my gut feeling is probably that there's still further refinement for this to be used as a real payment network. Okay, so let's talk about computer science. Let's talk about how we actually implement some of the basis of Bitcoin and related cryptocurrencies. And there's really 4 pieces to this, 4 big computer science areas of interest which come together with Bitcoin. There's hashing, there's the construction of the transaction blocks, which is you might have heard the word a blockchain, and that's really when we talk about chaining transactions together into blocks. That's what we mean, the construction of the ledger and the blockchain which it represents. Then we're going to talk about 2 other problems, the Byzantine generals, and finally Turing completeness of smart contracts. So, I should at this point I should say the hashing piece and the chaining of transaction blocks. This is fascinating in its own right, because this is how you create a network of people who all run computers that don't trust each other. It basically relies upon the idea that a good hash function is one way. So you can't, if you put in an input byte stream, the hash value for that byte stream you get out is not in any sense predictable. So if you make small changes to the input block, the output you get out will be wildly and radically different. And there's a theory of hashing which goes all the way back to the very first papers in information theory by Claude Shannon. So this goes back like till 1948, the basics of the unpredictability of hashing and what that means in the construction of algorithms which are called proof of work algorithms. Essentially, because good hash functions are so unpredictable, to produce a hash output that satisfies a particular property, and in the case of Bitcoin, what it is that the transaction block, when you hash it, it has to start with all zeros. That's the basis of the Bitcoin hashing algorithm. Because you can't predict how to get an output which starts all zeros, then what you have to do is you just have to keep trying. You have to keep working at it and keep going and going and going until you just happen by chance to find one. So that means that there's a statistical probability of how much work you have to do, how many computations you have to run before you find the magic block that actually works. So that's what's called in the jargon a proof of work algorithm. It says that on average you did this much work in order to compute this, and you can't cheat. There's no shortcut where a bad actor can say, well, okay, well I'll just pretend to do the work, and here's the next block which fits the criteria. Yeah, if you can't shortcut that. So other participants in the network, even if they don't trust you, they know you did the work. So that's basically how the Bitcoin network is set up. If this idea of chaining blocks together is confusing, then just pretend we're talking about Git. Yeah, because and in fact the Bitcoin blockchain is actually simpler than Git, because in the case of Git, a commit, which is equivalent to a block, a commit may have multiple parents, merge commits. In the Bitcoin blockchain, there is only one parent for each given node. So each block or each commit has only one parent. And then Bitcoin has a special algorithm for determining that if you have multiple forks, then actually the real Bitcoin blockchain is the longest one. That's again, for the experts in the audience, I've kind of massively oversimplified here, but that's the picture which I want new people to take away. Okay, so those are the first two pieces about hashing and how we build up the blockchain. They are both fascinating in their own right. Unfortunately, we don't have time to talk about them. The other problem here is what's called the Byzantine generals. And again, this is one of the classic problems in computer science. I mean, if you study the history of the Byzantine generals problem, you will run into the name and the work of so many of the great and the good of computer science. You know, Leslie Lamport, Barbara Liskov. You know, the list of people who've had something to do with the understanding of the Byzantine generals problem is very long and distinguished, and it's a fascinating area of study. It basically talks about how you deal with a situation where you have a distributed network and some bits of it might go bad or go wrong or go rogue, and that can be applied from everything from theory of how to reach consensus for disk arrays to the CAP theorem to network hardware. It's a very, very deep theorem, fascinating and beautiful in the computer science, but again, unfortunately, no time. So what we are going to focus on is the Turing completeness of smart contracts. And this, if you may remember, is what a Turing machine looks like. And a Turing machine is just an infinite tape with a program head, and you can move left and move right on the tape, and you can read and you can write. And of course, the reason why these things are famous is because of a work done by Alan Turing and Church, of course, to use this as a basis, a fundamental basis for computation. And there's a theorem which says that if you can have a programming language which is capable of modeling any specific Turing machine, and specific Turing machines are like programs, then a sufficiently complicated programming language, you can't be sure by looking at it, or there's no general purpose algorithm which takes a program as input and will tell you whether or not it terminates. And that's, of course, famously the halting problem. So this leads us to a problem because, okay, so Bitcoin has a very simple language on top of its ledger, and basically the language that we use to convey what we want to do in our transactions for Bitcoin is really very simple. It really doesn't give you a lot of ways to express yourself. So when people who had been working with Bitcoin started to think more deeply and think what they wanted to do for their own cryptocurrencies, they come up with this idea that what they wanted to do was to include a fully fledged programming language on top of the distributed ledger. So on top of a network that behaved a bit like the Bitcoin network, They wanted to add the ability to write fully fledged programs, and runs straight into the halting problem, because we're talking about a network of machines run by people that don't trust each other, and which Bitcoin has shown us very definitely will have hostile actors present on the network. So there will be bad people who will try to steal or misappropriate or damage the assets which are controlled by the ledger. It's not a trusted environment. So the problem then becomes, if we can write arbitrarily complex programs in our programming language on top of the ledger, what about Turing completeness? What happens if we, are we not giving up a load of control to people that we really don't trust here? So there's been a sort of question about what do we do about making our smart contract language? Is it Turing complete or is it not Turing complete? This is sort of the heart of the problem that I've started addressing. Okay, so let's just take that problem and kind of pause on it for a second. We'll come back to it and we'll see how to tackle it. And let's ask the question, okay, suppose we want to address this and we want to have a robust place to write our smart contract language. How does the JVM fit into this? Should we use the JVM? Should we not? Should we write our own virtual machine from scratch? How are we going to do all of this? So Java, of course, has been around for, wow, 22 years now. So from 95 to 2015. So it's been pretty well tested. It's kind of best defined, I think, by these two quotes from James Gosling. But it's a blue-collar language. It's a language for people, working programmers, that actually get the job done and actually deliver working code. That it's not supposed to be esoteric or particularly complex, but it's a straightforward language for building real applications, and that it's pretty simple. And the idea behind Java is that as little as possible is done in the actual language itself, and the class libraries and the sort of standard library that ships with Java is where a lot of the work is done. So we don't try to do too much, and we try to keep the core as minimal as possible. So that's the sort of language we're talking about here. It's kind of slow to change. It's pretty conservative in terms of its design. It doesn't want to rush off and add in the latest and greatest feature. You know, it's not like Scala. It tries to add in every possible language feature it can think of all at once. It's supposed to be simple. And in fact, here it is. This is the entirety of the Java language, every single keyword as of Java 8 on one slide. And this is quite incredible, because if you try to see this with other languages, if you, for example, do this with C++, I once gave this talk to a room full of C++ developers and asked them how many keywords, by comparison, C++ has. They got up to about 200, and then they started arguing with themselves about what should constitute a keyword. And it took me like 15 minutes to get the room back from them. So I'm not doing that again. For Java, it's 53. Here they all are. And they break down into a bunch of families. There's a family of flow control keywords. There's a family of literals and primitive types. I won't go through them all now, but this is pretty simple as a language goes. There's not much to understand here. Okay, so the language is small and compact, and we like that. We also have the JVM, and modern JVMs are really actually pretty well designed. There are really, I guess, 4 pieces to the JVM itself. Okay, we have the source code compiler off to the left here, which is the job of producing a class file, but that happens before runtime. At runtime, there are 4 systems to a JVM. You have a class loader, and a class loader's job is to get new code into the JVM. It's the only way in. If you want your code to run on a JVM, it has to be supplied as a class file, and you have to come through the class loading process without any errors or any faults. It's extremely picky about what it will let in, and class loaders are not forgiving things. You make even one error in that class file, and the class loader will kick you out. So that is a good security model. It's well implemented using this kind of single pinch point. We'll come back to that. That's actually a really important design feature for what we're going to do. Next up, of course, after class loading, hey, you passed, you're in the system. The methods that you want to execute are now present inside the JVM, and so the JVM interpreter kicks off. This is the bytecode interpreter, which is actually how the code is going to execute. You can run with this fine. You'll create objects in the heap, because all Java programs and all JVM programs do. And at some point, the garbage collector will kick in and deal with those objects which are no longer needed. That subsystem isn't shown on this diagram, but the other three are. So we have the GC, which is kind of running independently of this, which is the runtime representation of the heap. And then finally, the fourth subsystem is the JIT compiler, which is basically a way of improving performance. It's not mandatory. You don't have to have a JIT compiler. You can, in fact, just run with the interpreter. But the JIT compiler can provide high performance by compiling the code directly to machine code for you. But notice you don't have to have it. So what we've got here is we've got 4 independent subsystems. We've got a class loader that's responsible for the integrity of code which gets into the JVM. We've got an interpreter which is responsible for executing that code. We've got some go faster stripes in the form of the JIT compiler. And we've got a garbage collection process which runs separately from execution, which is just responsible for ensuring that memory as a resource is never exhausted. Okay, so what we've got here is a very clean separation of concerns. And sometimes people ask me, what's a separation of concerns? And I say, well, when I think about separation of concerns, I think about this. So if anyone ever asks you, a junior developer, to define separation of concerns, you feel free, have this picture and show it to them when they want to define why we separate our concerns and why we break up code into separated pieces with clear and very distinct responsibilities. So okay, so let's just have another look at the JVM diagram. We have our perimeter fence, basically our integrity checker in the class loader. And we have an execution subsystem in the interpreter. And then we have a housekeeping piece for the garbage collector and optionally a JIT compiler. Sounds like that might be a reasonable basis for a platform to run smart contracts on. So our design positives, I think are pretty clear. We have an interpreter which has very, very well understood semantics. It's been around for over 20 years. JVM bytecode is actually pretty simple because a lot of the complexity is present not in the bytecode itself, but in the class libraries. So if we can make the Java bytecode tractable, well, we've got to win, because all of the class libraries are written in Java bytecode. So basically, ensuring that the core of the JVM is sound and a good place for smart contracts basically is a much easier task than for other environments. The security model has been attacked for 20+ years, and okay, there have been bugs in the implementation. This is software; there are always bugs, and I think my favorite is the original Microsoft Xbox bootloader, which, when the very first one came out, it had 3 security-related bugs in 64 bytes of code. So every system has bugs in its implementation. But what hasn't happened is that in the 20 and more years that Java's security model and its approach to security has been attacked, no one has ever been able to find a design level flaw, that the model itself has withstood 20 years of attack. So if we want an environment which is designed for untrusted and designed for controlled execution, the security model of Java is a very, very good one. Okay, and going along with that, we also have the concept of class loading and the fact that everything which comes in has to be class loaded. So that provides us, first of all, with a pinch point. You have one entry point. So if you defend that, you've defended the whole system, which is well understood. And it's also a convenient point because it provides us, and the Java platform provides us with a way of extending class loading for our own advantage. So that looks like that might well be a place where the additional guarantees that we want our smart contracts to have, that we can add them there. And because Java has been so successful over the last 20 years, we also have a great tooling space. So we're not going to have to start from scratch, and there is already a wealth of open source tooling out there for handling and manipulating and dealing with JVM bytecode. So all of this looks great. Oh, and one thing which I should also say is that when we talk about smart contracts, they are very simple things. We're not talking about implementing an entire application container as a smart contract. A smart contract is going to be a pretty straightforward and simple piece of code. Probably, maybe a couple of hundred lines, maybe a few methods. Not really a lot of code at all. So it's okay for us to spend some resources on ensuring that they're sound, because the overall constraints of the programs we're going to run on top of this virtual machine are not huge. They are small things and pretty simple. Okay, sounds great. Let's do it. Well, not so fast. There are actually a few design negatives that we might also want to think about. Okay, so Java is the very, very dynamic environment, and that is potentially hard to reason about. The way that Java programs execute is that your bytecode is executed inside an interpreter. That interpreter is running on a thread inside a multi-threaded C++ application called the JVM. So effectively, all Java programs execute as part of a multi-threaded environment, because there are other VM threads that are operating. There are things which are doing profiling. There are things which are doing garbage collection. There are things which are listening for finalization. There are, if you just do a stack trace of a Java program, you will see that there are other threads besides the application ones. So that's a problem, because all multi-threaded programs are fundamentally non-deterministic. And if we want to be able to reason about what these programs do, we can't have that. So that at first seems to be a stumbling block. But then, if you read the specifications for the Java interpreter carefully enough, you will see that provided you stay away from certain things, the execution semantics are guaranteed. Now, one of the things that we obviously, when I say certain things, one of the things which we do need to have is that the smart contracts themselves must be single-threaded. Okay, we can't have a multi-threaded contract. As Java application code, these programs have to be single-threaded for them to be deterministic. And if they're not, we couldn't guarantee anything about the determinism. Okay, so that's our first big restriction, that the programs can't create their own threads, that the contracts have to just be bound into a single thread. Okay, so that seems to have dealt with the fact that the JVM is multi-threaded, but what about garbage collection? Garbage collection is non-deterministic. Okay, well that's true, but nothing which garbage collection do can affect the outcome of a program unless the program is somehow looking at the wall clock time in the outside world. Okay, but we don't actually want our programs to do that. We don't want them to be able to say they're dependent on runtime, because if we want these programs to give the same answer no matter where in the network they run, it shouldn't matter, for example, how fast or slow an individual machine is. The contract must still give the same answer, even when run on a slow machine versus a fast machine. So because of that, you can't just call the system clock. You can't look at the system clock and say, what's the time now at the start of the program, and call it again at the end of the program and say, what's the time now, and make some logic decision based on how long that duration was. So if you can't call to the outside world and look at the wall clock time, garbage collection doesn't matter either, because all it can do is affect how fast the program runs, not the overall outcomes, providing everything else is deterministic as well. Okay. Okay, so that seems to suggest that okay, we can't talk to the outside world, but we don't have to worry about garbage collection. What about JIT? Okay, well, it's possible that different runs could cause different programs, different methods within the program to be compiled. This is a standard problem with JIT. Even if you do a simple benchmarking run and look at which methods get compiled, it will be slightly different from run to run. It is that dynamic and that deterministic. So that could potentially, you might think that could cause us a problem. But two things here save us. First of all, JIT says that it must follow exactly the same semantics as interpreted. So if the interpreted code is deterministic, then the JITted code must be deterministic and give the same outputs. So that's a pretty strong statement that actually we're going to be okay with JIT. We can switch it off. Even in hotspot, we can pass a flag to the JVM and say just run in interpreted mode. So in fact, JIT is on the face of it looks like it should be something that we need to be really, really worried about. And in fact, it's one of the easiest things to deal with because the standards say that it shouldn't be a problem. And if we ever suspect that it might be, we can just switch it off without affecting our environment. Because once again, the smart contracts are very simple. And because they're very simple, they don't need very strict performance requirements. So running the smart contracts purely in interpreted mode would be an option for us as well. Okay, so that now sounds like we've qualified or we've dealt with most of the design negatives that we have for the smart contracts. So let's take a quick dive into bytecode. I can't see you, so I can't ask how many people already know some bytecode. I'm going to go reasonably quickly through this. The key point about bytecode is that it's actually pretty simple. On this last slide here, I've got a link to a thing called OcelotVM. If you have never played with bytecode before and would like to have a go, then repo, and there you will find Ocelot, and it is an implementation, simple implementation of part of a JVM bytecode interpreter. So you can see for yourself how an interpreter actually works by having a read of Ocelot and looking at the way that it's structured and just maybe read some of the test cases. Feedback and pull requests, very, very welcome. So here's what a class file looks like, if you've never seen one before. It's got, it's just a binary file. And you can probably see over here on the right-hand panel, there's a bunch of textual information and things which look a bit like strings and maybe some Java class names and some Java method names. And that's basically from an area of the class file called the constant pool, which stores all of the information that the JVM needs to figure out what this class is of. Very, very quick overview. Each opcode is 1 byte. That's why it's called bytecode. The opcodes run obviously from 0 to 255 because 1 byte. And about 200 of them are in use. And that sounds like a lot, but there's two things which happen to very greatly inflate the number of opcodes that are currently in use. First of all is that bytecode is typed. So there are 9 types in bytecode, 8 primitive types, and the A type, which stands for address, and it means objects. So there are certain sort of low-level operations, because of course the JVM interpreter is a stack machine. So it's operating on top of an evaluation stack. There are no registers. So you could, for example, load a value onto the top of the stack. Now, that immediately uses up 9 opcodes because you have to have a separate opcode for each individual type. So you have one opcode for byte, one for int, one for long, one for double, and one for objects. So that's 9 opcodes used up for what is basically one operation. So that inflation and the fact that some of the opcodes are typed across all possible 9 types means that you actually use up a lot of opcodes very, very quickly. JVM bytecode, compared to other types of bytecode, especially compared to the Ethereum virtual machine, is very simple. The operations which are here are all pretty low level. What we're going to do in a second is just to have a quick look at some of the main families of operations that happen, and each of them will be inflated by the varying actual opcodes that correspond to various types. It's an abstract representation. It is not machine code for an imaginary CPU. Bytecode does not look very much like machine code at all. And the sort of I guess this idea which came out when Java was young, that it's somehow a made-up CPU has been, it's one of those sort of urban legends or myths that survived way longer than it should have done. Okay, so if you want to run your code on the JVM, you need a class file, and inside your head, if you want to imagine what's going on with the interpreter when we're talking about this, just think of a switch statement inside a while loop. So the method is passed in as an array of bytes of bytecode, and you take the opcodes one at a time, look at what it is, and then switch on it. And then you find the opcode dispatch function, which is going to deal with that opcode, and then you do that one for that code. Then you reach the bottom of the loop, and if you haven't hit the end of the buffer, you go around and you take another byte from the byte stream. And there's a simple implementation of that in Ocelot if you want to take a look. So let's do a quick catalog of which bytes codes we're going to look at. I've mentioned that they come in families. Here are some of the load and store manipulation of values here. Sure enough, we have load and store. The arguments column shows you how many bytes follow the opcode. So for example, I might refer to iload followed by the byte 17. And that would say, take the value from the 17th local variable. Local variables in bytecode are numbered from 0 to 255. And every local variable that you ever create in a Java method is turned into one of those 255 local variables, which are present in the local variable table for this method. So iload 17 would say take the local variable from position 17, which is an int, and put it on top of the stack. Store would do the reverse, taking something off the stack and putting it in a local variable. Get field and put field, you use those for taking values on and off the stack and putting them into the fields of objects which are contained in the heap. So for get field, for example, you would take an object that was on the stack, look up the field that was contained in it, which corresponded to the 2 bytes of argument, and replace the object with the value that was contained in the field. And put field would do the same thing. It would take the value and the object, look at which field reference needed to be updated, and then set that field to the appropriate value. We'll see an example of this in a sec. These are the arithmetic operations. They don't have arguments. Instead, what you do is you put the 2 values on the stack and then issue an opcode. So for example, I put a double on the stack, I put another double on the stack, and then I issue a dadd, which adds the 2 together, takes the 2 values off the top of the stack and replaces it with the result of doing the arithmetic. So there's a bunch of different arithmetic operations. Obviously, they only work on the 6 integral types that are present. There are 8 primitive types. Obviously, you can't do arithmetic on booleans, and you can't do arithmetic on chars because they're not integer types. So each of these opcodes represents 6 separate opcodes. Flow control. Flow control in the JVM is really, really easy. There are no for loops or while loops anymore. Instead, everything has been boiled away to just ifs and go-tos. Okay, for switch statements, there's a couple of others for switch statements, but that's it. Even the JSR and RET opcodes, which used to be used, they have now been deprecated. In Java, as it stands today, all of your looping constructs and all of your flow control is done with if and go-to. The invocation of Java methods. This is done by one of 4 opcodes, or well, 5. But one of them, invoke dynamic, is the new one, which only came out in Java 7, and it's sort of weird and special. It's a whole talk and more besides in its own right. So we won't talk about that one. Instead, we'll talk about the 4 method invocation opcodes, which invoke static methods, virtual, which basically calls regular methods. If you want to call a method on an interface type, So suppose I've got something like map m equals new hash map, and then I call m.put. The static type of m is an interface type, so that will show up in the bytecode as an invoke interface. So basically that's the distinction. If the static type of a variable is interface rather than class, then you'll get an invoke interface. If the static type is a class, you'll get an invoke virtual. There's also invoke special, which is used for dealing with methods that can't be overridden, for things like supercalls and constructors. So that's a quick description of what your method calls will be turned into. And then there's a couple of other ones which you need to know about. These are particularly relevant for what we're about to do with class loading. These are new, which allocate the memory. So if you create, every time you create a new object, there'll be a new opcode which allocates the memory, and then the constructor body will be called as basically as a method. So the bodies of your constructors will be turned into special methods inside the class file. And when you call the constructor, there'll actually be a sequence of bytecodes where you new up an object, and then afterwards you actually call the constructor as a separate operation. So that's new. And also we have monitor enter and monitor exit. As you can probably guess, this is the bytecode level representation of synchronized blocks. So when you have a synchronized block in Java inside a method, it will be turned into a monitor enter at the start of the block and a monitor exit at the end of the block. We'll see those in action as well in a sec. There's also the shortcut forms. This basically is just a way of saving space. It also greatly inflates the number of opcodes which are in use. So let's take a quick look at this just so you've seen some bytecode. Here we have a very straightforward, simple class. It's got one field which is an int, and it's got a getter and a setter for that. We disassemble this to show the bytecode using -c, and it produces some simple methods. Notice that it also produces a constructor. So everything that you were told right from the first time you learnt Java, that if you don't write a constructor, which we didn't, that you will get one anyway. And sure enough, there it is. There is the body of the constructor that's been created. After the comment here, you can see which method it's actually calling, because what appears in the bytecode is just a number, which is an offset to tell you which method we're calling. And it's helpfully, the disassembler has helpfully turned that back into the actual method we're going to call. It's a method called angle brackets init, and hopefully it's pretty obvious that what that means is that that's the method that the constructor body gets turned into. Let's have a quick look at the getter and a setter. So this basically is going to load this onto the stack, and then it's going to use the get field opcode with two parameters, which is referring to the individual field, to get that, and then returns the resulting value back to caller. So let's see it in action. We load this onto the stack. We execute get field, which takes the object off and replaces it with the value of the field. And back it comes to caller. Okay, so far so good. For the setter, we have to do something slightly different. We load up this. We load up the int, which came as from the first local variable. Notice that the 0th local variable is this, at least for instance methods. The first local variable is the first parameter. So for a setter, of course, that will be the int argument. We now call put field, which takes both elements that were on the stack and sets the field accordingly. Now, of course, there's nothing to do, so we return, and oh look, the stack's empty. So there is no value to return, and as there's no value to return, it doesn't have a type, which is why void is not considered a type in Java, because what it's really saying is that the JVM stack machine had nothing on it when the method returned. So it's an absence of any value, and absences of values don't have types. So here we have the constructor, which basically loads up this, and then it calls the superclass constructor. So notice that invoke special is there to call a superclass. We also create objects in a slightly strange way, because what we do is we do the new, which allocates the memory. We do a dupe to duplicate reference, and then we call the invoke special to run the constructor body. The reason behind this, of course, is that the invoke instructions consume objects from the references from the stack. So if you don't duplicate, then what happens is you invoke special, and you've just destroyed the only reference you had to the object you just allocated. So you always duplicate it, so there are 2 copies on top of the stack. Only one of them is eaten by the invoke, and so you still have a reference to a new object left there. So when you look at bytecode, there's a very clear new dupe invoke pattern, which is always present. And that's one of the telltale signs how you can always spot where objects are being created if you're looking at bytecode, if you don't have the source. That was a real whirlwind through class loading. I hope that was okay for everybody. So let's talk about class loading. So the class file anatomy is pretty simple. It's a binary format. It's not human readable, but it is parsable, and it's actually not too bad to parse. The sections of the file are like this. There's a version. There's the constant pools. There are descriptions of interfaces which the class implements and the superclass, and of course any fields and methods that are present. This is how I remember it. You ever seen the movie Gremlins? This kind of gremlin cat is how I remember what the sections of the class file are and the order that they come in. So let's take one of these classes and load it in. In order to do that, we need to understand how class loading actually works. It is the process by which we take a class file, which is just some dumb bytes lying around on disk, and take it into something which actually is available to a running JVM. The essential point here is we're going to take in a class as an array of bytes, and somehow at the end of it, we are going to get out a class object. This is the only way to get a hold of a class object, is to start with bytes and run it through a class loader. There's no other way to create new class objects. The JVM's libraries are very carefully designed to not allow you to create a class object in any other way. Oh, and one other thing to notice, many frameworks actually transform classes as they're loaded. So the custom class loading aspect that we'll talk about does allow us to transform a class as it is being loaded and before it's made available to the JVM. We'll see how. So the first step is to just pull the bytes off disk and do some very basic consistency checks on it. That's sometimes called the loading phase. The real power happens in the linking phase. The linking phase basically does verification and then prepares and initializes the code. So the subphases of them, the verification is by far the most important. It basically ensures that this class file doesn't try to cheat and do anything that it's not supposed to do, that it doesn't try to circumvent the security model, and it also checks as much as it can up front. So in other languages, you might have to have a load of runtime checks about arrays and things like that, and if there were illegal accesses, you would have to try to detect them at runtime. But a lot of that can be done up front by the JVM at class loading time. The bytecode is very extensively checked. You check that methods are called with the correct static types. You check that you don't try to call a method that's expecting an int with an object, for example. You check that this class, as it's coming in, it's not trying to call somebody else's private methods, and so on and so forth. So the verification is quite extensive. At this point, we also have the stack nature of the JVM. We can check the state of the stack at every point in a method and ensure that all type information is correct, and that we don't try to do things like add an int to an object, which would be some kind of pointer arithmetic. All of that could be checked at loading time. So this is a really, really important piece of the JVM, and this is why we're going to build our stuff on top of it. One other thing which we also need to know about, because this is relevant to our case as well, is that a class file can refer to types that the JVM doesn't know about yet. Sometimes, before we can trust this class, well, hey, it's referring to another class over there that we don't know about yet. So we can only trust this class if that other class is trustworthy. So sometimes during the loading process, you kick off and you have to go and load another class before you can finish loading the first one. And so you end up with what's called the transitive closure of types from class loading, which basically looks a bit like this. I mean, obviously, we don't really do this with object because object is in our t.jar. But can you see how if you were to load object, you would have to load class because of get class. You'd have to load string because of toString. You'd have to load interrupted exception because of the wait, and clone not supported from clonable. But each of those classes has other dependencies. Class depends upon class loader. Strings implement both the comparable interface and the char sequence interface, and so on and so on. So actually just loading a single class can cause a huge amount of class loading to be kicked off. And that's something that when we build our class loader, we're going to need to take a look at. If all of the verification passes, you prepare, you get ready to initialize. But notice that until this point, we have still not run a single byte of code from the class that's coming in. And it's still possible at this stage for a class to be rejected. Finally, we finally initialize. At this point, you run the static initializers, you have a class object, and you've successfully loaded the class. So there's a huge amount of work which goes on. And it's only at the very end that we actually start to trust the class even a little bit. Okay, so what causes all of this magic to happen? It's a class called class loader. It's an abstract class, and it provides a mechanism called load class. So you pass in the name of the class you want to resolve and to load it, and load class will load it up for you. The way this works is that we actually have a hierarchy of class loaders. So each class loader has what it refers to as its parent. So each instance of class loader has another instance that it usually tries first. So normally the way that this works is you ask your parent class loader if it can load the class, and only if it fails to do so do you take matters into your own hands. This is how we fit in our own class loaders into this hierarchy by kind of following these rules and being a well-behaved class loader. The one that you're probably most familiar with is called the application class loader. It's the one which loads your application. Some texts, unfortunately, call it the system class loader. Please don't do that, because the system class loader is the thing which loads our t.jar, and that's actually properly called the primordial, just right at the top there. So this is our sort of standard view of class loaders that we have. And the user class loaders or custom class loaders are kind of down here below this dotted line. And the class loaders that we're going to write for our secure environment are going to go down there as well. So we need to make a custom subclass of class loader. And this actually is a fully fledged and working class loader. Doesn't do anything, and it's not very useful, but it does work, and it is actually fully fledged as a class loader. And notice that what we're doing is that when we create it, we are saying that we're going to call the superclass constructor, passing in the class loader which is responsible for loading the class myLoader. So basically, whatever class loader loaded the myLoader class, that should be passed as the class loader that we're going to supply to our parent. It's just a convention inside of how the class loader framework works. Every class loader I've ever written followed this rule, so it's really just a piece of boilerplate. Okay, so now let's talk about the two mechanisms that we have, which are actually going to be the ones that we use for our class loader. There's load class. Okay, that's the standard means, but what we want is to plug into the mechanism in a way which works. So there's another method that we override instead of load class. We override a method called find class, and find class is the hook that the class loading framework provides. If you look at the source for class loader, you will see that the find class method on class loader just throws class not found exception. Okay, so if we instead override in custom class loader, rather than throwing a class not found exception, we can do the work for our class to do what we need to when we're looking for this class. So that's our hook, and so we are definitely going to want to override find class. Also, we are going to want to actually have access to a method called define class. This is the thing which does the work. This takes in a byte array and it gives back a class object. This is a protected method, so it can't be called except from the same package or from a subclass. Class loader is in Java lang, so we can only call it from a subclass. And this basically is the hook we're going to use for our bytecode transformation. Okay, so now we're starting to get the pieces together. We know a bit about bytecode, we know a bit about class loading. We're starting to bring together the threads for how we're actually going to write a production grade class loader for this. One more thing we need is the ASM library. ASM is a bytecode library which enables you to manipulate abstract data structures which correspond to your class files. Bytes, we can stream it out. This basically is going to enable us to work with the data structures and the class as though it was data. It's a very mature library. It's been very well tested. There's even a cut down version of it that hides inside the Java 8 runtime. We're actually going to use the one which is a complete open source library. We don't touch the internals of the JVM, so we'll use the external library form instead. And what we're going to do is we're going to use an API that it provides, which is based upon the visitor pattern. So how does it work? Well, very simple generation is to just spin up a class writer and then call methods on it to write out the header, write out any methods and constructors, and then convert the visitor into a byte array and save it to disk. That would then provide you with a class file which could be loaded by any other Java VM, and it would not need the ASM library as runtime support. So that's key. When we're loading class files which have been generated from ASM, they don't make reference to the ASM libraries themselves. They are totally standalone and they can work just on any old JVM. If you want to see the basics of how we do this, I've got an article on InfoQ which shows us how to write class files from scratch using ASM, class files which have no source level representation. A slightly more complex pattern with ASM, and the one that we're actually going to use is this one here. We're going to take in one class file, we are going to read it, and we are going to rewrite it with a visitor before writing it out as a byte stream in a modified form. So we're actually going to do a transformation of one class into a modified form from inside our class loader. Okay, so let's put all this together and talk about what we're going to do to our smart contracts. What we're going to do is we are going to have a class loader which rejects anything which it can show is non-deterministic. Okay, so if you try to send us a smart contract that tries to create a thread or tries to look at the system clock time or does anything else which we know is non-deterministic, the class loader will just reject you. Okay, so that's the first thing. The second thing we're going to do is we're then going to take another pass over the class file and we are going to transform it. And we're going to write into it resource tracking code to see how much resources it takes to run the program. Things like how often does it throw an exception? How much memory does it allocate? How much, how many times does it jump through a loop? I mean, so is it going to try to somehow never terminate because it gets into an infinite loop? So we'll track all of that. And only once we've done that, load their class. Okay, so then that contract has been accepted and it has been modified so that we can keep an eye on it. Then at the runtime, we're going to have a container which allows you to execute that contract, but it monitors the resource usage. If the contract attempts to violate any resource limits, you just roll it back. So anything which is provably non-deterministic never gets in, and anything which tries to take advantage of the environment to just waste loads of resources will be killed, and the contract will be nullified and rolled back. So for people who are familiar with Ethereum and who know about a thing called the DAO, this would absolutely have prevented the DAO from operating. So which is one of the interesting things which came out of the research when we were doing it. Okay, so let's meet the whitelisting class loader. there's a few reserved words in the Java language which we need to pay special attention to. Native. We're not allowing any native methods because everything which I've said here was about JVM bytecode. If you get into native code, all bets are off. So you can't call any native methods. The way that we're going to kill the contract is by throwing exception. You could call thread.stop, but for some fairly deep JVM reasons, you don't want to do that. So instead, the preferred equivalent is to call thread death. However, it is possible to catch that. So we have to look through the bytecode and see if you try to catch thread death and exclude you. So if you try to catch thread death or throwable or something like that, no, you can't run. Synchronized. Although your contracts can only be single-threaded, it still makes sense to remove the synchronization keyword. So what we'll do is we'll go through, and if you see synchronized on a method or on a block, we'll just get rid of it. One other one which you might not have thought about is strict FP. The JVM actually runs floating point to whatever precision the hardware allows. So that could vary from machine to machine. Java and the JVM actually has a mechanism to force you to follow precise IEEE 754 64-bit floating point and nothing else. And that keyword is strict FP. So we turn that on globally. And interestingly, if you've been following the Java news, it looks like the strict FP definition will be switched back on globally in Java 10. So this is actually an interesting kind of related to forthcoming Java things as well. But anyway, we're going to do that. So we'll modify the bytecode there as well. So now let's see where the demo is. Okay, can you see the IDE? Is this large enough?
Yep, that's
yes. Hopefully.
Yep.
Okay, so here is our whitelisting class loader, and sure enough, it's a regular class loader. It's got a couple of caches, which are the loaded classes, which we store as both class objects and as byte arrays. Because we're not loading from the class path, we actually want to have additional internal class paths, which we're going to use to search for our jars and our classes. We've got a couple of class loaders, constructors that we're going to use, and they're actually only accessed from outside by factories. Okay, so here is the find class. This is our implementation of how we actually hook to find our classes. So this method will be called back by the main class loading mechanism. We check to see if we've already got a version of this class. If we have, then we hand it back. Now, it might be the case that we are not subclassing class loader. So we might not be subclassing some other class loader, like a web app class loader. So we actually need to call our superclass implementation to see whether or not it can load the class we've been asked for. Obviously, if you directly extend class loader, then that won't be the case. So if our parent class loader can't find it, we're going to end up straight back here again. So assuming that that's the case, we're now in a position where we want to load this ourselves. So what we want to do is locate the class file and then scan it. And the scan determines whether or not the class is deterministic. If it is deterministic, then what we do is we continue. We resolve where the class file actually is. So this scan method has basically done the first pass over the class file and is really asking the question, do you do anything which is obviously non-deterministic? If you do, you get rejected. If not, then what we do is we find where the bytes are on disk, read them back, and then instrument them. So what we now have is some transformed bytes, which has got our resource tracking code in it, and we can now call define class with the instrumented bytes, and that will create us with our transformed contract, which is ready to run. Okay, one thing I haven't mentioned is this flag, which has kept cropping up, called remove non-deterministic methods. And here is sort of something we discovered along the way. We discovered that, of course, people want to write fairly simple contracts, but they still need some basic data structures. They still need hash maps. They still need array lists and so forth. So we identified a subset of the JDK which looks like it might be useful. And I did some exploratory research to find out, not looking at class level, but looking at method level, how much of the JDK is deterministic. And the answer is a useful subset. So we actually added a second mode to the class loader, which, rather than just rejecting non-deterministic classes, it will produce a strict version of a class which removes any non-deterministic methods in it. So from that, we can create a transformed version of the JDK, which includes a substantial chunk of Java util and java.txt and a few other bits and pieces, which your contracts can call. So you can code against the standard Java APIs and still have collections and still have basic things that you might want for your contracts without losing determinism. And we actually ship that. We actually use the class loader to run against the JDK repeatedly until we built up a complete map of everything inside the JDK, which could be non-deterministic. And we save that as a runtime jar which can be used. So all of that actually means that the contracts are actually reasonably capable. Okay, so that was a side discussion. So let's just look at the scan method briefly. We spin up a whitelist checking class visitor. So here is an ASM visitor, which is going to step through the class. It's going to do things like it's going to check each basic metadata. It's going to check and make sure that for every method that we find, we switch on the strict FP. So remember how I said the strict FP was going to be forcibly switched on? Sure enough, it's getting switched on here. Oh, one other thing, we will need to disallow finalizers. Finalizers are intrinsically non-deterministic because they run as part of the garbage collector. So because of that, anything which implements finalize is definitely not allowed. So we have this class called definitely disallowed method visitor, which we use to kick out things which we know that we don't want. We then go through and check the bytecode of individual methods. So in here, you can see that we've got things like, we'll get rid of thread death. So anything which attempts to catch thread death is going to be kicked out. We don't allow invoke dynamic for technical reasons. Visiting the method, we step through and we look at all of the methods that this method references. If this method references only deterministic methods, it is itself deterministic. If none of the other checks have failed, then and it refers to things which are all deterministic, it's deterministic too. And that's the basis of the graph algorithm we use for stepping through to determine which methods are okay. Once we've done each method on a class, we end up in this method here, which is visit end, and we step through all of the methods and check to see what's happened. If a method is disallowed, we make the class not loadable, and we tell you why. Otherwise, if it's deterministic, we set that it's fine, and back we go. Now, there's one other wrinkle, which is, remember that I said that classes can refer to other classes which aren't loaded yet. So there is actually a recursive path which is possible through the class loader, where the class loader identifies, well, this class might be deterministic, but it relies upon that class over there which I haven't seen yet. So what that will then do is it will recursively kick off class loading in order to try to emulate the view that you need to load all of the classes which this class depends upon. So there is some sophistication in here. Okay, so that's the checking pass. Apart from scan, we also now have the instrumentation pass. So notice this is 2 complete passes over the class file. Here's the instrument with costs. What we have is we read the class in. We've got a writer which knows about how to rewrite class names, because one of the things that we need to do is, because we're going to be including things like Java util, we obviously can't have that as the package name at runtime. So we actually rewrite that into what we call the sandbox, where we prefix the names of all the packages with sandbox to get around some of the special magicness that comes from packages which start Java. So that's just a detail for that. And then what we do is we now introduce the instrumenting method visitor. So this has a type name called the runtime cost counter, which is basically just a place where lots of static methods are going to live for each counter. So this basically is a low-level API for visiting individual bytecodes. Monitor enter and monitor exit; those were the synchronized ones. What we do is we replace those with a pop opcode. Because the monitor enter, you put an object onto the stack, and then you call monitor enter to say lock on the object that's on top of the stack. If we're not going to bother with the locking, all we need to do instead of calling monitor enter is to replace the monitor enter opcode with just pop. And pop just throws away what's on top of the stack. So that's a piece of rewriting we do there. If we're going to throw, we're going to add in an opcode static. So basically, this is going to invoke the record throw. So this is a piece of telemetry or monitoring code to account for the throw that we've just done. We go through and we've got, for example, this one where we are allocating a primitive array. So now we record the array allocation and we say how much we allocated. We have a regular allocation, which is just for a single object. So we record that. We have new array, so we record an array allocation there. We also record jumps and method calls as well. So all of this stuff gets written into the bytecode, and then we return back from it the byte array. So this takes in a byte array and it returns a transformed byte array. Notice it also has a methods to remove, so it can get rid of anything on the way through as well. Okay, so with all of that done, we now have a loaded class. So now what we need to do is we need a container to run it in. So this is a container that I wrote called Greymorkin. Greymorkin is the name of a witch's cat. I don't know where I was going with this. Witch's cat, tomcat, something like that. And what this does is it sits and watches a directory. The directory basically will see incoming classes, which are the contracts. The directory watcher will pick them up one at a time and stick them on a queue. When this class notices that it's got a new contract, it will load them, check to see if they will actually load properly. If they will, then that means that they passed determinism and they have now been instrumented. So the resulting class object, CLZ, is then bound up into a contract object, which has got the code object itself as a class and a thread where it's going to execute. Remember, all of these are single-threaded, so it's just going to execute on that thread. We now check to make sure that the contract is viable, which is basically just a check to ensure that the code will run properly. And if it is, you set up its thread, start it, and put it onto a holder for some threads. Okay, one more thing we need is something to simulate the ledger. So this is a vetted log appender. Now, this basically is an append-only log, similar to the ledger, where you can only put stuff on it if you are a deterministic class. So only contracts which have passed the class loading process will actually be allowed to run here. So this is just a simple, effectively, rather than dealing with the full complexity of a full distributed ledger, this is designed to just simulate the process. Okay, so now comes the moment of truth where I actually start it up. Let's see if this works. Okay. So let's start up the logger. And it's watching this directory here, Gray-Malkin test. Over here, I happen to have a few classes I made earlier. So let's take a look at one of these. Let's take a look at simple one.class. Okay, so you can see pretty clearly this thing is pretty deterministic. It implements the interface we need to add to the log. So let's just and look at the output. So we saw the file come in up here. It added to the processing queue. This is all in debug mode, so you can see what's going on. Read the class. Check the first method. Check add one, add entry. Yeah, that also looks fine. Saving it. Saving the sandbox version. Check to see if the contract is viable. It is. So now execute the contract. We run the contract, and what you can see is that we call the method call, and the log appender, which simulates our contract, has received that entry and accepted it, and then it spits out the contents of the log. So far, so good. Have a look at what's in 2. Yeah, 2 looks pretty good too. So let's copy simple 2 over and see what the... So once again, this thing is pretty fast. It's found the second class, it's parsed it, and once again, it's printed out the actual contents of the log there. Okay, just to prove this actually works, let's do one more. This one, of course, has no possibility of working because, not least of which, it calls current time millis. So this one should be rejected because current time millis is not deterministic. So let's see about that, see if that does what it claims. So okay, it's tried to read this one. And it's failed. It's trying to load string builder, which is not a deterministic class. So sure enough, it's kicked it out because of the class not found exception at this point here. Okay, so there we go. That is a simple example of how we do deterministic and non-deterministic calls. And that basically pretty much brings me to the end. I've overrun a little bit. I'm sorry for trying to pour so much in to a short amount of time. The overall work for this is commissioned by a company called R3 as part of a project called Corda. There's an article I wrote for InfoQ which outlines some more of this, and some of the things I glossed over and didn't have time to go into. It was a piece of research that took me about 3 months. It's available. I don't think it's been fully merged into their mainline yet, but I think that's just waiting on a pull request. So thank you so much for taking the time out and being patient with the extended runtime. I've got a bunch of books and videos and so forth available. I'm also hoping to have a trip to Australia next year. So I've been talking to some of the guys in the Melbourne Jug. If you'd be interested in hearing about when I'm going to be in Australia, if you want to have me come and do some speaking or some teaching, or even give a hand with some performance issues you might have, then let your leadership team know. And I'd love to hear from some people, and hopefully I'll come and see you in person sometime next year.
Terrific. Thanks very much, Ben. That was fantastic, Ben. We'll end the broadcast and wind the broadcast up here.
Okay.